So imagine managing a Kubernetes cluster so massive that it has almost about 130,000 nodes. That is literally twice the size of Google Kubernetes Engine's tested limit of today. Sounds impossible, right? Well, Google just proved that it's possible. And today we are diving deep into how did Google make this possible. All right, let's start with the big picture. Why does Google even care about 130,000 node clusters? The answer is simple, and it is artificial intelligence. Right now, the world is in an AI arms race, training massive language models, running inference at scale, and doing reinforcement learning requires an insane amount of compute. Google's largest customers are currently running almost about 20,000 to 65,000 nodes per cluster, and the demand keeps increasing day by day. But here's the thing, there's a fascinating shift that is occurring in the infrastructure world. We are no longer constrained by chip supply. We actually now have enough GPU power. What we are constrained by is the electric power. Think about it, a single NVIDIA GB200 GPU requires 2700 watts of power. Now imagine thousands of these running simultaneously on a single cluster. We are talking about hundreds of megawatts of power. This is not something you can fit in one data center anymore. This is why Google and other cloud providers are now moving towards multi-cluster solutions that distribute power across different data centers. But before you can do that, we need to understand what are the limits of a single cluster itself. And that is exactly what Google set out to do. Their goal was simple, to push GK to its absolute breaking point and to its absolute breaking limit and learn along the way. This knowledge is very crucial because it directly impacts how cloud infrastructure is built for the future. Now, when you are dealing with 130,000 nodes, you are not just scaling up linearly. Everything breaks in new and interesting ways. So first, imagine trying to schedule 1 million pods on a single cluster, not one at a time. This goes on at a massive scale, at almost 1,000 pods per second. The Kubernetes API server now has to handle thousands of API requests, a load of API requests for creating pods, binding decisions from the scheduler, health checks, status updates, and object storage operations. All of this happening continuously at an unprecedented scale. Here is a specific pain point. When there are almost about 130,000 nodes sending health checks continuously to the API server, there will be almost about 3,000 to 13,000 queries per second. And these queries are just for these updates. These updates are nothing but the health checks that a node gives to the API server to tell that the node is alive. If the database cannot handle this, the entire cluster becomes unstable. Nodes might get marked as dead even when they are alive. Pods get evicted unnecessarily and the entire system falls apart. By the end of Google's experiment, they had almost about 1 million Kubernetes objects in their database. This includes pods, nodes, leases, and all the metadata that is associated with them. At that scale, simple database queries become bottlenecks. Even a quick query of list all pods on a certain node will lead to a cascade of problems. The Kubernetes control plane, which is the brain of the cluster, has to be responsive all the time. Operators need to query the status of their workloads. The scheduler needs to make placement decisions related to pods, and all the controllers need to coordinate. Overwhelming the control plane and nothing works, everything starts breaking. There are some features that are already included in Kubernetes. So the first major feature addresses read amplification. The problem where every read request hits the database, multiplying load and causing latency. Kubernetes includes consistent reads from cache feature to serve strongly consistent data directly from its in-memory cache. This reduces database load dramatically. Think about it. If you have 130,000 nodes, each of them is periodically checking the API server for pod status. That is thousands of redundant database queries coming onto the server. Now they are hitting the in-memory cache instead. But there is more. Sometimes operators need to query historical data as well. For example, show me what pods existed at resource version 5000. Instead of rebuilding the list from the database, Kubernetes has another feature which is the snapshotable API server cache. So the snapshotable API server cache feature is something where the API server keeps a B-tree snapshot of its cache at a certain point of time. This snapshot is incredibly efficient. It lets you paginate through all the historical data without even touching the database. The result, both filtered reads and historical lists are served without touching the database. The database barely gets touched and the system is blazing fast. This is essential for maintaining cluster-wide health at an extreme scale. Alright, so caching helps with reads, but what about writes? You also need to write data to the database. That is where the second innovation comes in. Google did not use a standard SQL database for the 130,000 cluster. They relied on a custom key value store based on Google Spanner, which is their distributed database. This distributed database spans multiple geographic regions. Why? Because Spanner is exactly built for this problem: massively distributed, highly consistent, and fault tolerant. Here is a concrete example of why this matters. Kubernetes nodes send out release updates every 10 seconds to tell the control plane that a certain node is alive. At 130,000 nodes, it will be 13,000 queries per second or 13,000 release updates per second, which are being sent to the API server. With a traditional database, this would be absolutely catastrophic. The disk I/O alone would max out. But with Spanner's distributed design, these writes can be parallelized across multiple different servers. Google confirmed that even at this insane throughput, the database showed no signs of being a bottleneck. This is critical because try to understand, if the node is not able to write its status into the database, it will be marked incorrectly as dead, and if it is marked as dead, the entire system becomes unstable. Spanner's solid architecture ensures that the critical heartbeat of a cluster never misses. Now, here is something important. Kubernetes default scheduler works at the pod level. It just asks where should this pod go, and the scheduler will do some placement decision and send the pod to a certain node. But with AI workloads, you do not think about individual pods. We think about jobs. A certain job would require multiple pods and multiple resources to run. It could be a training job or a batch processing job, but we think about jobs when it comes to AI. This is where Q comes in. Q is a job level queuing controller that sits on top of Kubernetes. It does sophisticated things like fair sharing. Each team or each job gets their fair share of resources. Priority based admission. High priority jobs get resources first. All or nothing scheduling. Either a job gets all the resources that it requires to get executed, or it would be waiting in a queue. No partial execution of any of the jobs. In Google's benchmark, they had three different categories of jobs or three different priorities of jobs that they have. So first is the low priority jobs, which would be batch processing jobs. Then they have medium priority jobs, which would be core training jobs, and high priority jobs, which are user facing inference services. Q manage the interplay between all these kinds of categories of priority. When a high priority inference job comes up, then it preempts the job which is currently going on and is of a low priority. It will preempt that job, send it to wait state, and it will allow the high priority job to get all of its resources and start executing. During phase 2 of the benchmark, Q preempted almost 39,000 pods in just 93 seconds. That's almost 745 pods per second. That is incredibly efficient resource allocation. Alright, so this system was built, but did it actually work? This was actually found out using a 4-phase benchmark that simulates real-world AI workloads. So phase 1, Google started with a clean cluster and deployed a single massive job. That it was 130,000 medium priority jobs running simultaneously. The result, all 130,000 pods were created and scheduled in 3 minutes and 40 seconds. That is establishing a baseline for pod startup latency and scheduling throughput on a completely clean cluster. Phase 2. Now they introduced real world chaos. Started with 650 low priority jobs, which almost required about 65,000 pods, taking up 50% of the cluster capacity. Then added 8 large medium priority fine tuning jobs, which require almost 104,000 pods, and it took up 80% of the cluster capacity. Along with that, it also preempted 60% of batch processing jobs. Now watch what the system does here. 39,000 pods are being preempted in 93 seconds. The scheduler handles an average of 745 pods per second of churn. Batch jobs are evicted, fine-tuning jobs are admitted instantly. This is where Q shows its value for itself about the default Kubernetes scheduler. Instead of gradually trying to reschedule jobs, Q makes its decisions based on its all or nothing algorithm, and it starts to evict or preempt the batch processing jobs and starts giving resources to the fine tuning jobs, admitting them almost instantly. Now, phase 3, high priority inference workload arrives, 26,000 pods. Again, Q preempts the remaining batch processing jobs. Then the inference workload scales up to almost 52,000 pods, which is almost 40% of the cluster capacity, to simulate a traffic spike. This requires preempting a part of the fine tuning jobs as well. Google ran a 10-minute traffic simulation to measure real-world performance under load. And the result, the 99th percentile pod startup latency for the inference workload was almost about 10 seconds. For the latency-sensitive service, that is excellent. Now, in phase 4, finally the inference workload was scaled down by 50%, and it was measured how the system recovered. In this case, as it was expected, Q automatically admitted the fine-tuning jobs that were preempted back into the cluster. The result of all of this, resources were efficiently recovered and then reallocated. Nothing sat idle. So let's look at the actual numbers of this benchmark. So the Google Kubernetes engine, which is the GKE, sustained about 1,000 operations per second, both for pod creation as well as pod binding, which means the scheduler is making placement decisions at an incredible rate. For comparison, most production-grade Kubernetes clusters handle up to 10 to 50 pods per second on an average, which means the performance here was almost 20 to 100x better. Even while scheduling thousands of pods per second, the latency stayed quite low. Just look at it, in phase 4, we had seen that for even for the 99th percentile pod to come up, it just took 10 seconds. This means services could quickly scale to rising demand spikes. And here's what is amazing. The thing that we had observed earlier, the thing that we had predicted earlier is that the control plane would go haywire. But here, despite all of the chaos, the control plane was completely stable. The API server latencies for the GET and list operations stayed well below the threshold level. In this case as well, the database contained over 1 million Kubernetes objects, but it didn't break a sweat. API responses remained consistent across all of the operations, be it get, post, patch, delete, whatever. This is the real achievement, but handling scale by maintaining stability and responsiveness. Remember those leads updates that I had mentioned? At full scale, the system was actually handling 13,000 queries per second without any bottlenecks. This is the heartbeat of the cluster, and it never missed a beat. So why should you actually care about 130,000 node cluster? Here are the practical implications. So firstly, multi-cluster orchestration. This research proves that single clusters can be scaled up to 100,000 plus nodes. But the real future is multi-cluster solutions where the AI workloads are actually being parallelized across multiple different data centers so as to handle the power load that we had discussed. The next one is workload aware scheduling. So there's a shift towards job level scheduling from pod level scheduling. So currently, Kubernetes works mainly on pod level scheduling, but what the future demands is we need multiple pods, we need multiple nodes to be used at a certain point of time due to multiple AI training jobs. And for that, we need to move towards job level scheduling. This means the scheduler will now understand this entire job as a single unit and make placement decisions for the entire job on a job level. It will optimize its decisions based on the entire job. So here is something important. These innovations don't just help manage mega clusters, but it also allows an average cluster to perform better in terms of fault tolerance, in terms of being resilient. So even if you are running a modest 100 node cluster, from this entire system or the entire architecture that has been built, we obviously can optimize that cluster itself, even though there are only 100 nodes, but the performance of a cluster can be optimized at a very good level. The improvements in caching, storage, and scheduling trickle down to everyone. Remember the power constraint? We are now in a world where electric power is the constraint, is the limitation that we need to optimize, but not the computing or networking. This fundamentally changes of how we think about building cloud platforms. So there you have it. The innovations in read optimizations, distributed storage, and job level orchestration all came together.